We're now into Chapter 3, and Chapter 3 is now taking those derivatives that we learned how to do in Chapter 2, and we're going to try to do something with it. Why did we spend all this time? Well, we spent time so that we could use that to help us make sense of a graph, create a graph, make something visual, that sort of thing. So we're going to start 4 goals today. Extreme value theorem, EVT, for lack of a better term. We'll use this a little bit, EVT. Extreme value theorem basically says if you have a continuous function, you got to be able to draw it without picking up your pencil. So you got to have a continuous function. And it's got to include the endpoints of your interval. So from A to B, x being A to B being x values, and we'll use this blue, this orange, and this red picture that you can see below it. If you can draw a continuous function without picking up your pencil, much like this blue, this orange, and these red graphs, there has to be an absolute highest value, an absolute maximum, and there also has to be an absolute minimum. If you draw a continuous function, I would dare you try drawing a continuous function that doesn't have a highest or a lowest value. So that's what extreme value theorem says. When we look at these 3 graphs, we're gonna use them to help us understand the difference between different types of extrema. Extrema being the plural of extreme. So relative extrema, absolute extrema, and then we're going to talk along the way about what critical values are. So the difference, but before we're done with this lesson, you got to understand the difference between relative and absolute extrema, and we'll have an idea what critical values are. So if we scroll down here and we look at our examples, okay? So I'm going to focus in on the difference between the blue, the orange, and the red graphs. Okay? We look at these things, extrema, again, highest and lowest values. If I told you, go to the blue function and find its absolute highest value, I would bet that you would look right there. That would be your absolute maximum. This would be your absolute minimum. Look at the orange one. Here's your absolute minimum, and here's your absolute maximum. Look at the red one. Well, the red one doesn't have any personality. It's just a straight line. Absolute minimum, absolute maximum. So looking at graphs like that, absolute means there's nothing higher or lower. Okay? I think that's the one that's most descriptive. It's got to be the highest. It's got to be the lowest. There's no exceptions. There's no. It's the top of the mountain or it's the bottom of the valley, whatever it happens to look like. Relative extrema is a little bit different. Relative extrema can only occur at critical numbers. At critical numbers. What are critical numbers? Critical numbers are places where the derivative is either equal to 0 or undefined. Places where the derivative is either equal to 0 or undefined. So when you look at this, well, we've spent a lot of time talking about things like horizontal tangents. Well, how many horizontal tangents would this blue graph have? Well, this would be a horizontal tangent. That would be a relative maximum, relative minimum, relative maximum, relative minimum. But notice the endpoint values, they don't mean anything. So these red ones would all be relative extrema. The high ones would be relative maximums. The low ones would be relative minimums. In the orange graph, there would be one relative minimum. And there would be no relative maximums because there's no, they're looking for horizontal tangents. We're looking for the top of a hill. We're looking for the bottom of a valley. The red graph has no relative extrema. Has none whatsoever. No relative extrema because there's no peaks and valleys. We're talking about just a line. Relative extrema have to happen at the top of a hill or at the bottom of a valley. How that hill or valley looks don't matter, but it has to happen at one of those values, critical values, horizontal or vertical tangents. Local extrema is any kind of maximum or minimum. So local extrema, if we were going to try to define it, any high or low. Okay, so local extrema. If we go and we look at the blue graph would have 1, 2, 3, 4, 5, 6. I got to move this out of the way. Sorry, that still didn't work. Local extrema. The orange graph would have 1, 2, 3 local extrema, and the red graph would have 1, 2 local extrema. So when we look at this, what we got going here, a local is anything that's high or low compared to what we have. So local extrema could be at an end, could be in the middle someplace, but if you notice, when you take a look at what we've got going on each of these graphs, the circles ended up happening in a lot of the same places. The circles all happened either at the top of a hill, or bottom of a valley, or on one of the endpoints. So the thing I'd like to sum up for us, extrema happen at one of two places. Endpoints, actually I'm going to do this in a color other than purple so that we don't mix it up, and either at endpoints or critical numbers. Endpoints or critical numbers. So that's going to be the idea of extrema. Now, how does it look if we put it in practice? Well, when we put it in practice and I look at this problem, find the extrema of this function. So here's what we're going to look at. If extrema happen at one of two places, either endpoints or critical numbers, here's what we know. Well, this thing's endpoints are -1 and 3. So I'm going to check f of -1. I'm going to check f of 3. I'm going to compare those values. Critical numbers. Well, I'd have to find the derivative before I could do anything with that, so let's find f prime of x. Well, how about 2 minus, 2/3 times 3 would be 2x to the -1/3, and if I clean that up, the negative exponent thing messes me up. 2 minus 2 over x to the 1/3. How about 2x to the 1/3? I'm doing a common denominator right now, over x to the 1/3. So there's so critical numbers. If I set the numerator equal to 0, in other words, I'm finding my horizontal tangent, set your numerator equal to 0. Let's see, 2x to the 1/3 is equal to 2, x to the 1/3 is equal to 1, cube both sides, x would be equal to 1. And if I wanted to find my vertical tangents, I'd set the denominator equal to 0, x to the 1/3 is equal to 0, cube both sides, x would be equal to 0. So here are your places where you might have maxes and mins. You might have a maximum at x equals -1 or x equals 3 because those are your endpoints. You might also have a maximum or a minimum at f of, we found 1 because that was one of our critical numbers, or f of 0 because that's one of our other critical numbers. So what we're going to do then, take those values, plug them in this original function. If you plug -1 into that original function, f of -1, well, let's see. F of -1, -1 times 2 is -2. -1 squared, and then cube rooted. -1 squared would be 1. Cube rooted that would still be 1. Multiply it by 3. How about -2 plus -3? How about -5? F of 3, if you plug it in, 2 times 3 is 6. Well, I'll tell you what, I'm going to give you this number. This comes out to be about -0.24. F of 1 is going to turn out to be -1, and f of 0 is going to turn out to be 0. So when I look at this, the highest value, the highest green value that you see, the highest y value, would be 0. And the lowest one would be -5. And then along the way, we'd have a -0.24, which is going to be hard for me to graph. Sorry, that's not where that one is. That one should be at -1. My apologies for the mistake. And then this one would be at -24. Well, if you make this graph, now remember, a horizontal tangent means the graph is smooth. vertical tangent, if the value exists, and in this case it does, this would mean it's sharp. So here's what your graph looks like. Sharp, smooth. There's what my graph looks like. And if I look at this, so what are the extrema? Well, it looks like our absolute minimum value would be at the point -1, -5. That'd be our absolute min. And our absolute maximum value would be at the point 0, 0. What are these other values? Well, this one would be a relative min, and this one would be this one over this right endpoint at x equals 3. This would be nothing. Actually, you know what? Let's change that. Let's call that thing a local max, because compared to the points around it, it is the highest, but it's not absolute, and it can't be relative because it's not an endpoint. So there's your idea of extrema. We're moving on.